Hey, everybody, this is Larry. This is day 22 of the 30-day Leetcode challenge. This is week 4 already. How did you do? Uh, hit the like button, hit the subscribe button, leave comments, leave questions, whatever you like, and then let's get started. Subarray sum equals k. Given an array of integers and integer k, you need to find a total number of contiguous subarray whose sum equals to k. Nums is equal to 1, 1, 1, k is equal to 2. Okay. So the first thing I would think about when I look at this problem is that when you think about sum and what does it mean, is that, well, what for me it's always about what are the edge cases, what are the constraints that may or may not create these edge cases. And for this, um, the range of the numbers in an array are -1,000 to 1,000. The length of the array is 1 to 20,000. So n is up to 20k. And the range of the integer k is, yeah, so that's the target. It could be a negative number. So I was gonna say if it's positive numbers, then you can do some, it makes it a easy proof to do some sort of rolling window, right? But now we will have to figure out, yeah, now we have to think a little bit deeper. And for this, there's actually not that hard, or well, it is actually tricky the first time I've seen it, but it is a problem that I've seen a number of times before, and this essentially comes down to sort of people classify this as a dynamic programming problem because we do kind of keep track of previous things, uh, but it's not a dynamic programming in the same way. This is also this is and we'll kind of talk about the analysis about this problem in a little bit, but this is also a pseudo polynomial dynamic programming problem, and what that means is that your running time will be dependent on your not just n, where n is the size of the input, but also the actual size of the input. Okay, and so the dynamic part about this, or dynamic programming part about this, is that now for every index, you look at, you count how many times from the previous or the ways that you've seen, how many indices that started, um, or how many different places can it start that ends here that sums to k. So that's the way I would phrase the dynamic programming subproblem. And okay, I mean they don't have one example, so it's a little hard to explain. But let's say you have okay, and let's make it slightly more interesting. Make it have some negative ones and so forth. But yeah, so now at every index, we ask ourselves the question, like from here, how many prefix, how many times does it, and just to simplify explaining this problem, let's set k to 0. Let's say we're trying to find a sum to 0, right? So how many times does it end on this index? How many prefix, how many indexes does it begin that sums the current index to 0? So that's the question I would ask. And then we could kind of keep track of that by keeping a running count. And so let's kind of do this. This is a little bit tricky, but not to worry. And for this, we're gonna use, at least in Python, something called collection.defaultDict, which allow us to just be a little bit easier to check whether to increment from previously. Yeah, now let's also have the answer, just keeping track of answers equals 0, return the answer. And now for nums, also keep track of the running sum. That's called running sum is equal to 0. That allows us to get the sum of the entire prefix. Yeah. Um, hmm. So I'm just trying to think about if there's a way to explain this in a clearer way. But yeah, so now running sum, well, let's set the first index to 0, right? So let's go to count 0 is equal to 1, which means that, and you could actually, maybe to be more explicit, call it running sum, so that basically, if you start from before the first index, then the sum is going to be 0. That's kind of what it is saying. And then the running sum that's added to the number. And then now, how do we get k from the current running sum, right? Um, well, how, so all we have to do is just do answer is first you go to the count of running sum minus k, or maybe k minus running sum. Um, the idea is that, okay, so some previous number, so some previous number is, okay, let's actually write it out then, it'll be more easy. So some previous number is equal to, because we want, so the formula we're trying to solve is running sum plus some previous number is equal to k, so minus running sum on both sides, so previous number is equal to that running sum, and yeah, previous is equal to, so that's kind of it, really. And that's our dynamic programming solution. Oops. Oh, well, yeah, of course. We forgot to, well, I forgot to uh, keep track of this. And then now we add 1 because that just to show that we've seen the previous running sum. And there are going to be edge cases, and we have to be thinking about it a little bit. Let's try, for example, here and 0. And there's a lot of zeros. Oops. Because 0 is probably going to be one of those edge cases to think about. So it's good that we're practicing. Okay. Also, because I wasn't sure whether I should keep track of the running sum before or afterwards. So maybe afterwards. Because you don't, I mean, it generally doesn't matter, but if you have zeros, then you don't want to count the current one as a 0 case. So that fixes this one, but maybe a little bit messes up the other ones. Those zeros, so this is, so we want at least, there should be at least 1 and 0, but oh, wait, this is not running sum, this is nums. I think that's why. Okay. This is slightly better, but obviously still a little bit off. Now let's kind of play with our debugging techniques then. We could just print count every time, I suppose, as a start. With the negative numbers, it's always going to be a little tricky. But yeah, first, yeah, the 0 has an index of 1. Well, oh, yeah, I mean, this doesn't matter. But it would make it slightly less verbose to print out. Yeah, so this is right. Because for 3, you want to add this sum for 1, and for 2, you want to add for sum for 0, and 1, well, negative 1 isn't in there. So this should be 2. We'll also just track the answer just for printing state, for printing reasons. So here, let's say there should be 1, and here there's there should be 2, and that's accurate. But here it should be 3, and then 4. Yeah, at least 4. I don't know where the 5 is, to be honest. 1, 2, 3, 4. Is there a 5? But I'm still wrong in either case. Maybe my formula is wrong. So current number is, okay. Let's say we have the current number is equal to plus some other previous is equal to k, right? So this should be right. But also I'm just double checking a second. Hang on. Okay, let's just do it for now. Previous. Why is my negative ones in? Oh, because this is returning 1. Am I thinking wrong? Because we want the index in the dictionary such that I guess it's good that I'm getting this practice then. Um, I wonder reverse running sum. Am I doing the running sum backwards? So so now we're giving a current number. In this case, we're given the number 1. We actually want to look up -1, which is fine, but that's not what we want, right? What we want, or in the index or in the lookup table, -1 is not going to show. What we want is the previous time where is 1, right? So did I get did I get the signs wrong? Give me a second to think about this. So 1, we want it the sum of the previous whatever to be -1. Am I filling this one? Okay. Let's make a simpler version of this so that I could kind of wrap my head around a little bit. And actually, I don't even need this really. This should be, yeah. So okay. So for the -1, we want the prefix that sums to 1. Maybe I have to include itself. Am I? This is running sum afterward. No, it still tries to get -1 because it's I think the first time I learned this, I was very confused too. This time I have a little bit of an issue with it. So this is the 0 version of it. Then the running sum is the prefix that you want to match, right? So the one if the previous is, so we want the previous to be 1, right? So that this minus the running sum is equal to 0. Is that right? Okay. I think I tried to add it when I was subtracting it maybe or something. Let's play around with this. I'm not confident right now. Whoops. Okay. I guess I didn't paste it. Okay, let's try another one. I think I got the signs wrong. Okay, so yeah, so sometimes these things is very easy to get the signs wrong, and clearly I did, because I think I got it wrong last time too. Because what we want is we want running sum minus. Okay, I think I got it. I just kind of mixed up the signs a little bit, or a lot, for a long time. But basically, what we have is, I think I'm just trying to find a way to better explain it, because I think I had this idea in the beginning, but then I mixed up the sign and then I confused myself a lot, which happens from time to time. And obviously, if you do that in an interview, always make sure you keep on articulating your thoughts and also just try your best. No panic. But yeah, but what we were doing was, in a way, calculating the prefix sum. Yeah. So for example, for this case, we have one. Well, let's say there's a 0 that starts in the beginning, but 1, 2, 3, 2, 1, 2, 3, 4, somewhere. Yeah. And then now you have a new number coming in. So let's say you have a -1. You actually want, for k is equal to 0, is this minus the prefix that will give you 0, right? I think I mixed it up by summing them, because now that I think about it, I don't know why I wrote previous plus the current running sum, because basically the idea is that you have two running sums. Let's say I have 2 pointers. You're looking at this index, then that means your running sum is here, and then you want another index where the sum of this portion minus the sum of some smaller portion is equal to k, or 0 in this case. So that means your equation is actually running sum, typo aside, sum minus previous is equal to k. And how many times that happened. And now that we're all coming running sums, you actually, and then this just becomes, well, actually the other way, depending on how. Previous is equal to, obviously now running sum minus k, and then now we just keep track of how many times we've seen that previous prefix sum. So that's pretty much it. I'm just trying to think a little bit. Usually I do get this very quickly. I mean, I think I got it recently in the code force. Um, there was a recent problem in the code force that I did something similar. But I think, yeah, signs are hard. I think even if you have the right idea, I think what I did wrong with kind of this video and what this problem was that I think I rushed it a little bit trying to solve it. And from that, uh, and I think if you look back on my video, I probably hand, I was a little bit too hand wavy. I was because I knew how to code it up. That I was not as strong in my foundation in explaining how and understanding how to get this problem. I've done it a few times, but maybe not enough times that it's autopilot. Though I thought I might have tried to. So definitely make sure you go slowly, pace yourself. You have 40 minutes. I've only took 20 minutes, but in an interview you may have 40 minutes, 60 minutes. Make sure you explain yours every step of the way and kind of yeah, don't watch too much, and also test, as you can see. Well, let me submit it first. But yeah, make sure you test. Make sure you do all these things, um, and yeah, and and yeah, the idea is using prefix sums, and the idea is using prefix sum and then look at what you've seen before prefix sum, and then keeping track and count on that, and then solving it that way. I mean, I was very close, but it took me about 20 minutes to debug because I got my formula wrong in my head a little bit. Um, and with dynamic programming, right, or dynamic programming problems, it's very easy to be a little because a lot of your code is going to look the same, um, but how you understand the problem determines your base cases, your transition states, your whatever. And there are a lot of things that, like you change a little bit in one way or one direction, and everything's different, right? So dynamic programming problems, you really have to clearly define what your states are, what are you looking for, and how to solve it. So yeah, so running time. Running time. This is going to be O of n, and it's easy to see why. This is O of n times. There's O of n, there's n items, and each of them does O of one operations. There's O of n space. I thought if you do a little bit, I mean, yeah, there is some stuff about. I think so. I did mention a little bit about pseudo polynomial for this reasons, because in theory, the space storage will depend on the domain of your array or your array element. And in this case, for example, it's, your domain is -1,000 to 1,000, which is fine because the range is up to 10 million or -10 million. But in theory, you can imagine a case where, well, if the numbers are unbound, then actually, because you need to keep the sum of it, it could actually be higher than O of n, right? You can imagine, just, I don't know, some crazy, like, if they're all integers or even like they're longs, you can overflow it and then you have to do store more numbers and stuff like that, or more than like log n per number or something like that. So it's a little hand wavy, but nonetheless, in this case, given these constraints, O of n is just your storage limit because at most you're going to have n running sums. So this is O of n space, O of n time, and here you go. That's the problem. It's a little bit tricky for me, but I think it's a good lesson to learn that, well, even people who are good-ish, that's up to you. You decide whether I'm good. But even people who are confident and have done it before, sometimes you really have to make sure you explain and have a clear thought about how you're attacking the problem. Because sometimes, especially with dynamic programming, and for me, sometimes binary search problems, where like I would spend way too much time on off by one because I took a little shortcut in the beginning and didn't really clarify my thought. And here, I was like, oh yeah, I've done this. I've done this a lot of times. It's just time programming. You just do a lookup table. And it's like, well, you're almost there. And it's true. I did, 95% of the work in like 3 minutes, and then I spent the next like 10 minutes debugging it because I was like, oh wait, I'm misunderstanding something because I thought I knew something, but I didn't. But yeah, but overall, I still figure out myself, so I'm okay. Yeah, let's take a look together at the hints to see if I miss anything fun. Will brute force work? No. Can we optimize by using? Okay. What about storing some frequency? Okay. Okay, this is essentially what we did. Okay, fine. Yeah, so overall, an interesting problem, but yeah, hope you did better than I did, but hope you also learned a little bit from it. Thanks for watching, and we'll see you tomorrow. Hit the subscribe button, and I do one of these every day. Maybe I should have said that at the beginning. Anyway, bye-bye.